Thank you very much. So thank you very much for this kind invitation. It's a very nice opportunity to talk here in the seminar. So the talk of today is a joint work with Aurélien Alfonsi from École des Ponts about approximation scheme for stochastic Volterra equations when the kernels of the stochastic Volterra equation are of completely monotone type. So, the outline of the talk, at first, I'm going to present the general framework of our study, and then maybe introduce some preliminary result. Then I will introduce our approximation method, which is, of course, will be general for a general stochastic Volterra equation. And then I will focus more when the kernel is of rough type, of course, and then we will maybe I will show you some numerical illustration on the specific rough Bergomi stochastic volatility model, and finally I'm going to present some numerical results on that. So the general framework that we considered in this case. So here we have a stochastic Volterra equation written in a very general form, where I have the drift coefficient, which is with a convolution kernel here G1, and the diffusion coefficient that is convoluted with a second kernel that may be different from the first one. Here I'm going to suppose that both coefficient B and sigma are globally Lipschitz. B can be vector sized, and the sigma could be have a matrix size, and W is a standard Brownian motion that may have different size, but here we prefer to take the same size for all the coefficients here. So our assumption on the kernel is that they are uniformly integrable on the interval 0t. So if I'm considering the so G1 and G2 are matrices, D times T matrices, and the matrix norms here should satisfy this uniform integrability with respect to time. So this is the main assumption on our kernels here. So let me be more precise. For this study, we will focus on specific kernel that can be written in this very particular form. So they can be written as a Laplace transform of some positive measure here, lambda. Here we can also, as we considered d times d dimension, we can also have some dependence on rho through matrices M1 and M2 to make, of course, the kernel as general as possible. But this provided that the norm on the rho parameters for the matrices we introduced here should be finite. Of course, here the lambda measure should satisfy this condition. So the lambda is a measure on R plus, and it should satisfy, it is the Laplace, the J bar here should be finite. So the Laplace transform of this measure on 0 plus infinity should be finite for every t. So as you can see here, a first remark that we can make is that since both kernels J here can be easily upper bounded thanks to this upper bound on the matrix M, can be upper bounded by the G bar here, upper bound, then we need to assume that the G bar have finite second order integral, so that our previous assumption is satisfied. Let me recall you, our previous assumption is this one, both kernel are uniformly integrable with respect to time. So then here, of course, we will assume this assumption. So a kernel that can be written as a Laplace transform of a positive measure like this one is a kernel that is of course called in the literature a completely monotone kernel. So that's why in the title of the talk is stochastic Volterra equation with completely monotone type kernels, because we treat, of course, the multi-dimensional problem, and we have this additional multiplicative matrix Mg that appears here in the kernel. So if we consider the simple case dimension d equal 1, then our kernel, stated here, are exactly of completely monotone behavior. So as an example for this kernel, we have the famous RAF kernel, famous in finance. So the RAF kernel is of course a power t to the power h minus 1/2 for h between 0 and 1/2. If h is in this range between 0 and 1/2, then it's clear that one can write of course the kernel as a Laplace transform of some positive measure that is noticed here in this talk as a lambda h, and the lambda h is nothing but the power of rho to the power minus h minus 1/2 up to some multiplicative constant ch here that depends on the gamma function of the parameter h here. So this is, of course, the example that we will focus on. However, our technical proofs, of course, cover a more general setting. And of course, we will focus more and more at the end on the RAF kernel case. So let me show you first a preliminary result here. Now, if I now consider a specific measure, lambda, which is a discrete sum here of some Dirac points up to some multiplicative coefficients alpha I, and if I have an order between the rho I here, and if I suppose that the rank of the matrices alpha 1, m1, rho 1, etc. Is equal d, so that we are sure that x0 can be written in terms of this, decomposed in terms of this matrices that depends on rho I, then the solution of the original stochastic Volterra equation 1 can be explicitly written as follows. Xt can be written as a sum of x rho I t plus a second sum, of course depending on the multiplicative coefficient here, and y rho it. Why this is interesting? Because if you look carefully here, the component x rho I and y rho I are here, of course, Markovian components, SD satisfying stochastic differential equations that can be, of course, so we recover the Markovian setting. So this is a very important remark, that if you consider the original stochastic Volterra equation, and if you replace the specific the lambda by a discrete sum of Dirac weights here, then you end up with a Markov system of stochastic differential equation. So now I can show you the approximation method we propose in this work. So now there is a first step in our approximation is called the truncation step. If you remember, well, we have our kernel is defined as an integral on a Laplace transform on R plus of the measure lambda, of course. Here we first take some truncation constant k and introduce the blue term here, the truncated kernel that is integrated on the specific interval 0k of this Laplace transform. And then we introduce the associated stochastic convolution equation that we noticed here, xk. So xk is solution to the stochastic Volterra equation, but with the truncated kernels here, G1K and G2K. And the first result, due to this approximation to this truncation step, is the following. If we assume that lambda is a positive measure, such that this quantity R of k is our truncation constant, is the double integral on the remaining term, k plus infinity, of 1 over rho 1 plus rho 2 of lambda d rho 1, lambda d rho 2 is finite, so this is called our assumption H1. If this assumption H1 is satisfied, then we are able to quantify the error that we made using this truncation procedure. The error behaves like R of k. Okay, so this is a first source of error when truncating the kernel. So let's have a look on this truncation error in the particular case of the rough kernel. So if I consider the red kernel, which is the rough one that is given here, recall that in this case the truncated kernel G is simply the integral between 0 and k on the interval 0 and k of the Laplace transform of this measure. Then we can compute explicitly the upper bound R of k that behaves like k to the power minus 2h. So here the strong error associated to the truncation procedure behaves like k to the power minus h. So this is the first source of our approximation scheme due to the truncation. Now, of course, once we truncated, we want to approximate the truncated kernel. So let us consider first G hat k, of course of J here, a given approximation. It's not precise yet here, but a given approximation of the truncated kernel GKJ for J between 1 and 2, because here we simply consider two different kernels, but you can assume that you have the same kernel and you can omit easily the index J here. So we define for t between 0 and maturity the error between our approximation, the kernel here, the approximated kernel, truncated kernel, and the truncated one. Okay, so we have an approximation of the truncated kernel and the truncated kernel. And we want to assume that there exists some delta bar that is uniformly integrable, the second moment of delta bar is integrable between 0 and t, and such that this quantity for both kernels, the error between the approximation and for the approximation of the truncated kernel, is upper bounded by this delta bar. If so this is we call this our assumption H2. Now we consider, as before, x hat of k is the associated stochastic Volterra equation when replacing the kernel by the approximation g hat of k, of course, here. So here we introduce our approximation. Sorry, here there are typos because here it's a b of x hat and ds, and this is sigma of x hat dws. Sorry for the typo. So you have to imagine that you simply take, yes, this stochastic differential equation, and here you replace by gk by the g hat k, g1k by the g1 hat k, and g2k by the g2 hat k. Okay, so let us recall our assumption that are introduced so far. The first one is the upper bound for the truncation step that is given by the R of k upper bound here, and the second one is the error that we suppose to be known on, of course, the approximation truncated kernel and the truncated one. Then we have a first result, and the assumption H2, we are able to prove that we have uniform bounds of moment, the second moment of the truncated approximated stochastic Volterra equation. So under the assumption 2, we have this moment, second moment finite. And we have the following proposition. Still under assumption H2, we are able to prove the existence of a positive constant that depends, of course, on the parameters of the problem, the starting point, maturity, the B0, so the B0 and sigma 0, L, M1 and M2 are the associated to the kernel, and such that for all t between 0 and maturity, we have a control on the approximated stochastic Volterra, truncated stochastic Volterra equation and the truncated stochastic Volterra equation that behaves like a delta 1 hat k plus delta 2 hat k integrated between 0 and t. So now, this is the second source of the error between the approximated kernel, truncated kernel, and the truncated stochastic Volterra equation here. Then, if we combine the both results for using the two source terms for the error, then we get the strong error theorem here. So if we assume that the measure lambda satisfies the assumption H1 and H2, then we are able to have an upper bound for the strong error between our original stochastic Volterra equation and our approximation of the truncated stochastic Volterra equation. So our strong error here behaves like L of k plus this upper bound that depends on this delta hat 1k and delta hat 2k. So this is the general result. Now let me specify it for the simple case of specific choice of lambda or of lambda. So let us assume for the moment that we have lambda that satisfies H1. So I'm considering here some a set of intervals of the form I minus 1 over n times k, I over n times k. And I'm considering these weights, rho I, in this interval. And let me at first consider a first naive approximation of our truncated kernel. So this naive approximation is based on using the weighted, the Dirac weights given by the rho I here. Each rho I belongs to each small interval of this type. And the weights alpha I here are simply corresponding, of course, to the measure of this interval with respect to our measure lambda. So this is our kernel, approximated kernel, and this is the approximation measure, as I told you. So this is a sum of Dirac points that are with this multiplicative constant that is simply the measure of each interval, the measure lambda of each small interval of this type. So if we take this very naive approximation, then there exists a constant c such that if we have enough points, n large enough, then the strong error between the original stochastic Volterra equation and the x hat k, so the strong error, behaves like our upper bound r of k. And now, so this is for, recall that this is the first constant is for the truncation, error, and the second one is due to the approximation because we use this specific sum of Dirac points. Then the error here behaves like k to the square over n squares times the measure of the whole interval 0k to the square. So clearly here a first result is that we have to choose r of k and this second constant to be, of course, proportional. So we have to choose n here to be proportional to k times the measure of the interval 0k divided by square root of r of k. So that the both errors contributes both errors contributes with the same in the same manner for the global error. So let me recall you here for this very specific case when I choose this particular choice of the discrete points here for the Dirac using the Dirac weights here. Recall that our preliminary result shows us that the associated stochastic Volterra is simply a system of stochastic differential equation. So means that here our approximation here can be, of course, is simulatable, and we have a simulatable approximation, and this is the error we have if we use such approximation. So now, what about considering at the same time, what about the rough kernel case? So as we keep still the naive approximation. So in the paper, we refer this as a Riemann approximation that is based on this n Dirac points with this multiplicative weights, the measure lambda of each small interval I of k, in. So for the rough kernel case, the previous result reads as follows. The strong error between the original stochastic Volterra equation and our naive approximation, that is a system of stochastic differential equation here in this case, behaves like k to the power minus 2h, k to the power 3 minus 2h over n squared. So here a reasonable choice of n turns to be, or of k, the truncation should behave like n to the power 2/3. So with this particular choice, you can see here that the strong error between the original stochastic Volterra equation and our approximation SDE system, the strong error behaves with a rate here of order 2/3 times h. So now let us focus more on the rough kernel case. So the aim of the talk now is to improve this 2/3 rate here. Here clearly the h here is of course something that is is connected of course to the regularity of the stochastic Volterra equation. So the h will still remain here. So our aim in what follows is to improve this this multiplicative rate constant, the 2/3 here. So the 2/3 we get it when, of course, we have this very naive approximation, which is the Riemann approximation. So as a first guess, what if we consider a kind of Simpson rule instead of so this was the first intuitive thing we thought about it, is what if we replace the Riemann approximation with the Simpson rule. So in this case, we did it in this way. So before instead of truncating between 0 and k, we first we consider two different intervals. We write 0k as 0k to the power beta. Okay, beta is between 0 and 1, and k to the power beta k. We write it in this way. Then on the interval 0k to the power beta, we use the naive Riemann approximation. And on the interval k to the power beta k, we use the Simpson rule here with this multiplicative constant based on this 1, 2, 3 points, with these 3 points that can be computed, of course, given explicitly here. So for the weights using on 0k to the power beta, the discretization on the 0k power beta, we use the same rule as before. So we consider intermediate point lying between these two bounds, I minus 1 over nk to the power beta and I over nk to the power beta. However, for the Simpson rule, the choice of the 3 points here are given by the following choice you see here. So okay, and now it's about optimization. We have to optimize the beta here for the truncation on the 0k to the power beta, the beta constant, and we have of course to choose the optimal truncation k in this case. So it turns out that the optimal beta is given in this case by this ratio 10 minus 6h over 13 minus 6h, and the optimal truncating constant should be given by the n to the power 13 minus 6h divided by 15 minus 6h. So if we choose such optimal truncation constants, then the strong error between, so here the x hat k is the stochastic Volterra, is the system, of course, of stochastic differential equation where we approximated the kernel, the measure lambda, by the lambda hat s with the Simpson rule. A first part with the Riemann rule and the second part with the Simpson rule. And then the strong error in this case, we improve the rate 2/3 as follows. It becomes 13 minus 6h over 15 minus 6h. So the worst that we can have in this case, for if you let h vary between 0 and 1/2, the worst rate we can have is 5/6, which is better than the 2/3 we had before. So this means that going and trying to improve the naive Riemann approximation will improve, of course, the approximation rate of our here discretization scheme. So then, having this in mind, we wanted to go, of course, further and we propose to use, of course, a Newton codes methods that generalize the Simpson rule at some order capital G. So let us fix a number j in n, integer number here, and the smooth function f. Let me recall you the Newton codes method for computing integral between bounds a and b. It is given by this sum between 0 and j of this particular points that of course should be chosen on each lying the C here is a point between a and b. So the Newton codes method on the interval will be only applied as before on the interval k to the power beta k, and on the interval 0 k beta we keep our Riemann trick, our Riemann sum. So in this case, the lambda hat Newton codes rewrites in this form. We have the first part, which is based on the Riemann approximation on the interval 0k to the power beta, and we have the approximation based on g plus 1 points now. G plus 1 points, of course, using this new rho I weights. The rho I weights are given by this choice on each moving interval between a small interval between k to the power beta and k. Of course, here, if you simply take the g capital G equal to, then you recover the previous setting of the Simpson rule. Okay, so this is our new approximation. And we have the following proposition. So let G this integer for the Newton codes method, and let us denote G hat K is our kernel, that is where we replace the lambda, the kernel lambda, by the Newton codes approximation. then it turns out that the optimal beta is given by this constant, and the optimal truncation constant k should be given by n to the power of this new constant 2. So this is done after an optimization procedure. If we consider such a choice for beta and k, then we are able to prove that the strong error between our system of stochastic differential equation based on the Newton-Cotes approximation of the kernel here and the original stochastic Volterra equation, of course for the specific rough kernel case, have a strong error of this order. So we get the minus 2h, of course, as in the previous cases, but the 2/3 and the 5/6 we obtained respectively in the Riemann with the Riemann and the Simpson rule are now improved by this constant. So if you look closer to this constant, this means that when letting g tends to infinity, if you take a very precise approximation for the kernel, means letting g tends to infinity, the ratio here tends to 1. So this means for any given epsilon between 0 and 1, I'm able to find a g for my Newton-Cotes method such that the strong error here behaves like n to the power minus h, which turns to be here the optimal rate that one can hope to get using this approximation in this case. Why? Because as I told you, the h here you can't, of course, easily get rid of it because this is implicitly connected to the regularity of the problem. So the hope and of course the aim we reached here is that we improve the coefficient here and make it closer and closer, very close to 1 in this case. So this is our main result. So now all this stuff is of course in the d-dimensional setting, or what we gave here in the d-dimensional setting. However, for the one-dimensional setting, more things can be done to improve approximation schemes. So what I'm going to present from now on is more helpful for or can be considered as a user guide for practitioner, because it gives some hints and some tricks to improve the numerical approximation, effective numerical approximation on a machine. So now let us consider and focus on the specific one-dimensional setting. So here in this case, we consider dimension d equal 1. Let us get rid of the constant m1 and m2 that appears in our kernels, so that now our kernel j are completely monotone kernels, because they are exactly Laplace transform of some given measure. And now, if we modify the choice of rho, if we take the rho in even for any of the approximations, so recall in the Riemann approximation or in the Simpson approximation or in the Newton-Cotes approximation, we still have a first part that relies on Riemann approximation, at least for the interval 0 k to the power beta. So if for this first part based on Riemann approximation, we take this particular choice for the weights rho in, which is given by the integral of rho lambda d rho on the interval I of k, divided by the measure of the interval I of k, then we are able to kill the first order in the approximation in each of our proposed approximation. So let me be more precise. So with this specific choice, if I consider the naive approximation, when I simply replace the lambda by the Riemann sum based on the Dirac weights, And now if I change this truncation function, the truncation constant, to be equal to n to the power 4/5, then the strong error here behaves as follows, and the rate is of the strong error is h2 times 4/5, which is clearly better simply by this choice, which is clearly better than the h times the 2/3 that we had before if we don't make this choice for rho I. Now, what about the Newton codes? If we do this for the Newton codes, then it turns out the optimal beta, of course, will change. It is given by this new constant that depends, of course, on the g. G is the number, of course, of the points that I'm going to use in my Newton codes approximation. H is the Hurst parameter. The new choice for k should be as follows. And then it turns out that the strong error behaves in this case as follows. So it is h times this ratio. So we have still the same behavior. It means that when I let g tends to infinity, so I take more and more points in my Newton codes approximation, then this turns to be equal to 1. So I recover the optimal rate. But for fixed g, we can notice by this new modification for the weights, at least for the weights that are involved in the first interval between 0 and k to the power beta, we improve the rate here. So this rate that you see here in red is better than the rate given before. So it's smaller than the rate given before here. So if we take, so it is written here down, so I hope you can see it. So we have clearly that we have a better rate than before by simply choosing the rho I and k given by this form. And of course, for the Simpson case, we get the new rate, which is h time of the strong error, which is h time 22 minus 4h divided by 25 minus 4h, which is at the worst case, since h is belonging to 0 1/2, so the worst for this rate is equal to 20 over 23, which is still better than the 5/5 we recovered by the Simpson rule. Of course, this is due to the fact to this particular choice of the weights on the first truncation interval between 0 and k beta. So this is the first trick, and that applies on the simple one-dimensional setting. So let me now move to the numerical results to illustrate, of course, what we obtained so far. So for the illustration, we consider, of course, the rough kernel, and we take a very specific stochastic Volterra equation that corresponds to a drift coefficient which is equal to 0 and diffusion coefficients equal to 1. This turns, so the stochastic Volterra equation will correspond to this stochastic integral here. And for this approximation, of course, we have in mind to apply, because this is, it's clearly connected to the volatility of the rough Bergomi model. So that's why we first focused on this specific case of stochastic Volterra equation. So it's very specific. And we propose to compare 1, 2, 3, 4 schemes approximation. Let's have a closer look on this 4 approximations. So the first one is x1 hat n, in which we approximate the kernel using the naive Riemann sum and using the weights, simple choice of the weights on each small interval between 0 and k. Recall that the theoretical result in this case yields as a strong convergence of order 2/3 times h. And then the second approximation scheme uses still the Riemann approximation, but combined now with a tricky choice of the weight rho I and k. As mentioned before in the previous result, in this case, the strong error would behave like here, like n to the power minus h times 4/5. And of course, we have to change our truncation constant. Of course, the optimization will change. So those are the two schemes, both based on Riemann approximation. We only change the choice of the weights in our sum of Dirac weights. Then let us move to the third approximation, which is the Simpson one, the Simpson rule, with a naive choice, let's say, for the weights on the Riemann approximation part. Recall that the lambda hat Simpson, there is still a Riemann approximation on the interval 0 k to the power beta, and the Simpson rule only applies on the k to the power beta k interval. So in this case, we propose a very simple choice, naive choice for the Riemann part approximation in the lambda hat S. In this case, the theoretical result we mentioned before gives us this rate. The strong error would behave like n to the power minus h times 13 minus 6h divided by 15 minus 6h. And the fourth and last scheme is the Simpson rule, but with this tricky weights for the first Riemann approximation. And if you remember from the previous result, we recover this, of course, better rate here for our strong error convergence in this case. So those are the four schemes. So what we are going to measure, we are going to measure the strong error. In this case, the strong error is given by the expectation of, so J here is of course from 1 to 4, depends on our approximation method that we will use. And we want to compute the second order of the error here, the second moment of the error that we noted here by zeta j n of t. So one thing to be noticed here is that this error can be explicitly computed. Why? Because it is simply based on this remark. So remember that the xt is simply given by this stochastic integral, because we are in a very specific case. And we want to approximate this, all our approximation scheme can be rewritten as follows, as some multiplicative constant times exponential, convoluted exponential here, convolution times dws. So clearly you can see that the difference here, of course, what will change if you change your scheme, it's only the rho n and of course the weight alpha I, that's it. But for any given alpha I and any weights rho here, you can see that this difference is a centered Gaussian random variable that have explicit variance, that is given by explicit matrix sigma that we can compute. So this means that we can simulate exactly this zeta of g of n of t. So this is what we did to compute the strong error. So there is no bias in our computation of the strong error in this case. So let me show you the first results. So as I said before, we computed explicitly the strong error for each of our four approximation schemes. Of course, we are expecting that this will behave like a multiplicative constant times n to the power minus 2h times to some factor gamma, and this factor gamma depends, the theoretical gamma depends on the choice of the method. So let us at first have a look to the naive method. Is based on simply Riemann sum without any particular choice for the weights of my Dirac sum in my Dirac sum. So we considered three Hurst parameter, 0.45, 0.25, and the most challenging one is 0.05. So we recover this errors each time, and we recover a good approximation of the theoretical rate gamma. So the theoretical one in this case using the naive is 2/3 as mentioned before, and here in our approximation we are able to find a good approximation of the theoretical factor. So we have the good rate. Let us move to the here we used 50 points. Let us move to the second approximation. The second approximation is still Riemann, but using the tricky choice of the weights, the Dirac weights rho. Then, as you can see here, the theoretical rate in this case, you remember it's 4/5. So, and our approximated rate is a very good approximation of the theoretical gamma factor. Let us move here with still less the third approximation. So here for the third approximation with less points, because of course it is more efficient approximation, we still recover a good approximation. So the theoretical factor in this case, of course, depends on h, if you remember well. Then those are the last line is the theoretical one, and the last but one line corresponds to our approximated rate that we can observe numerically, and we have good approximation of this rate, which seems which it turns to be confirming, I mean, our theoretical result. Same thing for the fourth scheme, the one based on Simpson with the tricky choice of the weights, my Dirac weights. We have good approximation here for the rate, so we recover our theoretical result. However, as you can notice, for all the four scheme, if even I take the most efficient scheme here, which corresponds to the fourth approximation, yes, we recover the good rate. However, if you look to the order of the strong convergence error, so zeta, let me recall you, zeta is the strong error, as you can see, for the most challenging case where we take the Hurst parameter very small and close to 0.05, then we have a constant error, which is not zero. So this is, of course, a bit annoying from a practical point of view to have a constant error. So as here we recovered the good rate, so this suggests it's not about the approximation scheme, but on the multiplicative constant we have in this approximation scheme. And this is a common problem, if I well understood, to many of the papers that exist in the literature. They may have exhibit a good rate, of course, and you have the rate of convergence, time a constant, and it seems that even with other approximation, this constant can be very large and sometimes even exploding. So now the aim, of course, is to get rid and to improve this error, because this is, of course, simply not acceptable, even if we have the good rate. So let us keep the rates, of course, because we've been optimal in this case, since if we take the Newton codes with g tending to infinity, we recover the strong rate of order n to the power minus h, approximately n to the power minus h. So this is optimal, but we have to do more and more works on, of course, on improving the multiplicative constant. So how we would proceed? So for this, we we propose a new a modified approximation that is called that we called a systematic approximation in this case. Sorry. Sorry, I have to skip the. Okay, so what is this systematic approximation and how it works? So, as before, we keep truncating. If I want to summarize in 2 words this systematic approximation, so I can summarize it in as follows. We have just to do a more to be more careful in our truncation procedure. So we keep truncating the integral here as above at k equal to n to the power gamma h for some gamma positive. And then use one of the previous discretization. You use Riemann or Simpson or Newton codes. It's up to you. However, we propose to go deep and deep in the truncation. So don't stop at the level 0k, but do more works on interval of types between k and a to the power n times k. So let us take a constant a larger than 1, and we propose even to approximate the above integral on the interval k a to the power nk. So go deeper in the truncation and don't stop for the truncation between 0 and k. This will improve the truncation constant. And we propose to use the same discretization rule as proposed previously in each small interval of this type, I to the power I minus 1k, I to the power ik, until we cover the whole interval between k and a to the power nk. So this trick will reduce the truncation error. Now let us define the corresponding approximation measure. Let us call it lambda hat a. So lambda hat a now is based on 2n points instead of n points. Okay, and here we can consider a Riemann sum, of course, but the very simple choice. But here the g hat k associated to this kernel is, of course, we recover the lambda hat a given here. So a first remark that we can have here that, of course, support this, that we have reduction of the truncation error, is that the new kernel that involves the new measure, approximation measure lambda hat a, is larger, is in between our previous approximation kernel and the target, I mean the true kernel. So means that we reduce the gap between g and g hat k if we use an approximation of g hat k a. But as you can notice here, there is still a gap here, and we want also to cover this gap. Then, at first, we propose to choose a star, the optimal a, to minimize the distance, here the distance between the true kernel and our approximated kernel integrated between 0 and t first. And then, as I told you before, as still we have a gap here. Of course, this is better than this one, clearly. But as we have still a gap here, we propose to multiply our kernel by a multiplicative constant xi here, and xi would be, of course, the one that minimizes this squared distance here, which very simple calculations gives you the optimal sigma that it turns to be equal to this ratio of integrals in this case. Okay, so we make two tricks. We go deeper in the truncation, okay, until a to the power nk, and we choose the a so that we reduce the second here second order of this moment of this integral, and we even multiply our kernel since we noticed that we are approximating the original kernel from below. So we can even use this multiplicative trick here with an optimal constant that makes the approximation more tight. And those are the numerical results that we recover in this case. So so here I'm just showing you the case for the Simpson rule. If you remember well, the theoretical factor was 4/5. And of course, here we still recover the rate. Of course, this procedure is not to improve the rate. We are done with the rate from our previous results. Here, it's only about to improve the approximation constant. If you remember, previously, we have constant 2 here for the challenging Hurst parameter case 005. Now, as you can see, we recover zeta here is of course our strong error that is close to 0, and if I'm considering more and more points, of course, I see that it converges to 0, which is of course very better, which is better than the previous case, and even interesting from a practical point of view. So let me now turn to the financial application. So we have in mind to apply this to the Raff-Bergomi model. So let me recall you the Raff-Bergomi model. So we have the stock price that satisfies this exponential here dynamic, where the volatility here nu s is an exponential of this stochastic integral we approximated before. And here we can consider, of course, a correlated Brownian motion, and it means that there is a correlation rho between the volatility, the noise of the volatility, and the noise of the stock price. Of course, the first thing to do is to approximate the stock price on some using some discretization scheme. Here we propose to use an Euler discretization. So then we freeze each time the coefficients here, and we simply have to compute the increments each time. And at the end of the day, what we have to do is to be able to approximate the vector of the volatility vector that appears here, okay, the nu n. And in order to compute the nu n, you need, of course, to compute this stochastic integral, and for this one we used our systematic approximation. This means that we kept here the kernel that is truncated with optimal constant a star, optimal constant xi star, and with the Simpson rule improved by the tricky choice of the Dirac weights. So this is the approximation for this integral that we plug in here in this exponential, and then plug in the whole approximation of the stock price. And there is another additional trick here we used that improved our approximation, is that instead of keeping this coefficient to be constant, we use the approximation here so that this exponential remains an exponential martingale. So, of course, this is tends to the t to the power 2h eta square half, But from a numerical point of view, it's better. We notice it that it is better to keep the approximation for this. Why? Because it keeps safe the martingale structure of the exponential. Sorry, here there is a missing xi star square in the second term. There is a typo here. So this is a numerical trick that improves really significantly our obtained numerical results. And now, once we have the stock price, we can compute, of course, the European option, and we prefer to show you here and to illustrate the implicit volatility call option here, implicit volatility of call option, using exponential strike of type exponential k, where k varies between minus 0.15 and 0.20, using Monte Carlo estimator. So here, as you can see, we used for the RAF Bergomi, we used the method proposed by Kebaier, Gavrol, and co-authors, using the explicit method. So the blue one you see here is the explicit method by Kebaier and co-authors. And our approximation based on stochastic differential equation is the one given in red here. Of course, improved, as I told you here. This is for the Simpson rule, simply 3 points. It's not a high-level Newton-Cotes method. It's simply a Simpson. Improved by the choice of the tricky choice of the weights of the my-Dirac sum, and improved by the truncation constant A star and xi stars. So this is the red approximation. So we stick here, at least for this range between 0.20 and minus 0.10, we really are very close to the explicit method. In yellow, you have the confidence interval for the Kebaier co-authors and co-authors methods. And in green, it's our confidence interval. And we took here the most challenging case that appears in this original paper by Christian. That corresponds to a very short maturity of given by 0.041. And of course here, so this is the illustration seems to be to fit very well the explicit method. Thank you very much.